Using the framework that I've presented in these videos for doing applied statistics, you see that anytime you do bivariate statistics, you need to look at shape, strength, and significance. What we need to do is we need to take a conceptual look at what those phrases mean. When we say these are 3 of the 4 things you can do with statistics, just what is it we're talking about? We need to understand a little bit of the nuts and bolts about them. So a conceptual understanding and a little bit of the nuts and bolts before we can look at any specific bivariate or simple multivariate tools. So in this framework that I've built that I'm using, which is very similar to the frameworks that most statisticians use, except that I'm leaning it more toward applied settings, the 4 things that we can do with statistics are sorted out according to what kind of analysis we're doing. If you're doing a univariate analysis, you just look at shape by custom. You can, in fact, do more things, but generally what people do is they just look at the shape of the patterns. When you move to 2-variable or simple multivariable analyses, though, you look at shape, strength, and significance, and in the case of simple multivariate, you also look at specification. Let's set specification aside for a later video, and let's just think about what do we mean by shape, strength, and significance when we're relating variable patterns to each other. So, shape, in its simplest form, means to compare and contrast. It means to say, when I have an independent variable, because I'm using a bivariate 2-variable approach here, when I have an independent variable and there's a pattern in it, I ask people if they're male or female, and there's a pattern. Some proportion of them are male, some proportion of them are female. And I try to find out if that's related to some particular outcome, their views of a particular social issue. Then I'm trying to see if the pattern in one variable, how the cases are distributed across the values, is related to the pattern in the other variable. And so we cross-tabulate these patterns, or we do comparison of means within categories of the independent variable, or we do other techniques that try to see if the pattern in one variable is related to the pattern in the other. The simplest version of shape in this case is to compare and contrast. Imagine, if you will, that we ask men and we ask women what they think about gun control. Whatever the question may be in a survey, there's some pattern of answers for the men, there's some pattern of answers for the women. And we can compare the pattern of answers for the men to the pattern of answers for the women. We're comparing, seeing how similar they are. And we can contrast them. We can see how different they are. So if we have a circumstance where 60% of men were in favor of a particular measure and 60% of women were in favor of that measure, we'd say they're very similar. But if we had 60% of men in favor of a particular measure and we had only 10% of women in favor of that measure, then we would say, well, they're quite different. So we look for the similarities and the differences in the answer patterns, if it's survey questions, for the categories of the independent variable. Now, normally, people are more interested in the differences between the categories of the independent variable than they are interested in the similarities. Because the reason they usually go looking at the analysis is because they think there are differences. But you should be careful to see if there are similarities and differences. When we do some live examples of a variety of different statistical tools, you'll have a chance to see some compare and contrast happening. Now, this is messy. It's not straightforward. It isn't elegant. It's actually rather clunky to compare and contrast, and it tends to have a lot more words, and it tends to be debatable exactly what should be emphasized. But particularly if you have nominal variables somewhere in the mix, or just categorical variables sometimes, you're forced into a compare and contrast approach. What most researchers would like to do, if the data will allow them, is they'd rather do shape in a form of direction of effect. That is to say, is there a tendency in how changes in one variable are related to changes in the other? This can only be done if both variables being analyzed, the 2 variables that we're seeing if they relate to each other, if both of them are ordinal or higher, or put the other way, neither is nominal. Neither is nominal. You can't have a nominal variable if you're going to talk about direction of effect. It's not a common mistake, but I do see it relatively often where someone tries to describe the relationship between two variables, and they talk about a direction of effect, and in fact what they're doing is they're working with a nominal variable in the mix, and it's nonsensical what they're saying. Now, direction of effect, much like compare and contrast, is used in a whole variety of statistical tools that we will look at in later videos. When we talk about direction of effect, we normally talk about positive relationships and negative relationships. And we're going to use those two words in a very different way here in statistical analysis than we use them elsewhere. The ways we usually use these two terms are we think about positive things being better and negative things being worse. So we say that was a positive or negative effect, meaning that it was a good or bad thing. In statistics, sometimes people use the words that way. Another way that we oftentimes use positive and negative is a sort of more or less. It's the number line. A negative change means that you go lower in value on the number line. And a positive change in something means you have an increased amount of it. You go up on the number line. That's also a way that positive and negative might be used in some statistical analysis. Somebody might say, well, the effect was positive, meaning not that it was a good thing, but that it was an increase. But to make matters more complicated, the most common way that we use positive and negative in statistical analysis is actually a different way, where we actually think in terms of the direction of change on each variable either being the same as the direction of change on the other variable, and that's called a positive relationship, examples coming, or the direction of change on one variable being opposite the direction of change on the other variable, and that's called a negative or inverse relationship. So this isn't what you're used to hearing, but this is what we use when we talk about a direction of effect. An easy way to think about this is think about your dependent variable and your independent variable, and just use this sentence in this form. You can't reverse these things and say it the other way around necessarily. You can generally, but not necessarily. As cases have higher values on the independent variable. Now remember, there's no nominal variables now. We can only have ordinal, interval, or ratio variables involved. As cases have more of whatever the independent variable measures, what happens to those cases on the dependent variable? Is there a trend? So as cases tend to have higher amounts of whatever the independent variable measures, do they then tend to also have higher amounts of what the dependent variable measures? That would mean more independent is related to more dependent. They're moving in the same direction. Both are increasing. It's a positive relationship. And by the way, that does mean if you have cases that are having less of the independent and they have less of the dependent, then there'll also be a positive relationship, right? It's not about more or less here. It's about moving in the same direction. But if you use this sentence, then you would say, as cases have higher values on the independent variable, what tends to happen to their values on the dependent variable? If they increase, and increase, it's a positive relationship. If they decrease on the dependent variable, you have an increasing amount of the independent variable leads to a decreasing amount of the dependent variable, then it's inverse or negative. If increasing amounts of the independent variable has no effect on the dependent variable, the more of the independent variable you have, nothing happens. People tend to all still have the same amounts of the dependent variable. More independent, same amounts of the dependent, then that's what the null hypothesis actually predicts, that there's no relationship. And sometimes we can have a curvilinear effect, which I'll exemplify in just a second. All right, so as people work more hours each week, I don't have data in front of me here. I'm just going to say plausibly, I think they would make more income. Not necessarily, right? We all recognize some people work more hours, they're salaried, but let's say that we have a bunch of hourly workers, and so as they work more hours, an increase in the amount of hours they work, they will make more income. So more of one is associated with more of the other. And you can see the direction of the line here as you move to the right, and as cases have a placement further to the right because they have more hours worked, what happens to their values, the trend line shows that they tend to have higher amounts of income. But we could say as people work more hours each week, they have less leisure time. So as we move to the right and people are increasing the amount of hours they're working each week, it means that the number of hours they have available for leisure goes down. As you move to the right, the trend line goes down. As people work more hours each week, let's hypothetically say, they basically eat the same meals they've always eaten. They still have breakfast and lunch and dinner the same way, snack the same amount, so their food consumption doesn't change. So as we move to the right now, as cases have higher amounts of hours worked, the calories that they actually consume, the average for all these cases, the trend line is it just stays the same. People who increase hours and move to the right will just keep having the same calories consumed. Or, as people work more hours each week, they feel more empowered at first. They feel like they're doing something, accomplishing something, getting somewhere, until they work so many hours that they start feeling less empowered. They feel trapped. They feel like they're a slave to their job. They have no life. And in this circumstance, you can see that I've just used a basic parabola here, but as you move to the right, you see people increasing their sense of personal empowerment until they reach a point where more hours, and now they're not working, they've gone from 10 to 20 to 30 hours to 40 hours. Now they're going to start saying, I'm going from 40 to 50 to 60 to 70, and I start feeling like I'm less empowered, like I'm trapped. And that would be a curvilinear relationship where as you increase on the independent variable, in some places it leads to an increase on the dependent, and in some places it leads to a decrease on the dependent. Okay, that's direction of effect. And in many of the tools that we're going to look at, direction of effect is how we interpret the shape of the relationship between the two variables. So you could find yourself, when you look at the patterns of two variables and how they relate to each other, you could look at them and compare and contrast the values on the dependent variable within the categories of the independent variable. We're going to do that in something called cross-tabulations. We're going to do that in something called comparison of means. Or we might look at a direction of effect, a tendency as there's an increase in the independent variable, there's either a positive effect on the dependent variable or a negative effect where it goes down. All right. So strength, conceptually, is trying to give us some idea of prediction mathematically. Usually what we have, most of our strength measures are basically finding one way or another to say, if we know values on the independent variable, does it help us to better predict values on the dependent variable? Imagine that I have 100 people standing in the hall, and I'm going to have them come in the door. And each of these people works a certain number of hours a week. And I can even tell you that these people work, somewhere between 0 and 50 hours a week. And I can tell you that on average, they work 41 hours a week. But when the first person comes in the door, you're going to make some guess, and you're going to probably be way off. You just don't know. As person after person after person walks in, you try to predict how many hours a week they work, you're just making wild guesses. If we had the mean, an average of 41 hours, we'd probably just guess the mean. But the point of the mean is that it's a type of midpoint, more to come in a later video, but the median or the mean, these midpoint kind of indicators, they're still going to have a lot of error in our ability to predict. But what if I told you that all the people waiting in the hall, that some of them are male, some of them are female, and a lot of the women have elected to stay home with their kids more so than a lot of the men have. So the men tend to, on average, work a lot more hours. They have an average number of hours of, say, 43, and the women have an average number of hours of 32. Now, when they walk through the door, if you guess the mean for each one, you guess the mean for the men, you guess the mean for the women, you're going to be closer. You're still going to have error. You're not going to hit exactly how many hours each person works, but your amount of error, the distance you are from correctly guessing the number of hours, is less. This is the idea, one way, mathematically, that we wrestle with the idea of strength of effect. All right. Now, strength of relationship, association, correlation, effect sizes, all four of these terms get used when we start talking about what I'm just calling strength. They don't all technically mean the same thing, but for a practical person working in a regular circumstance where they're just looking at a few variables and trying to answer a straightforward question, the terms can be used interchangeably. There are going to be several places in this video where any professional statisticians are going to just shake their head. And they're going to say, no, you can't do that. Actually, if you're a race car driver, you need to really understand how to control a car. If you're just commuting to work, you don't. If you need serious statistical work done, you need to hire somebody who really knows when and how and what to do. But if you're just looking at a few basic analyses in some applied setting to figure out if the program is working or if the customers are satisfied, you're just commuting to work. You just can use some of these basic tools. And at that level, you know, it's kind of interchangeable what we call them, even though professional statisticians are now going to disown me. All right. So now effect size can be measured a lot of different ways mathematically. Most of the tools that we use range from 0 to 1. Some do not. The ones that I'm going to use as examples right here, I'm not going to actually explain anything about them. I'm just going to name them. They're just going to be a bunch of cryptic names. But all of them range from 0 to 1. But there are others, Cohen's D, Hedges G, there are others that in fact don't range from 0 to 1, and you just have to be careful. So I'm going to make some recommendations in these videos of tools that you would stay with that are commonly available. They're available in the stats program that I'm going to use as an example. They're commonly available, and they're really not likely to lead you astray. Now, for the ones that range from 0 to 1, we can't always use the same rules of thumb of what's a big effect and what's a small effect, but for many of them, we have some rough guidelines. All of us who do statistics for a living don't agree on exactly where we draw those lines, and in fact, it's a little more complicated than we might wish, but we're just commuting to work here. We're not driving a race car. We don't need to have a really clear understanding of friction coefficients based on the kind of rubber on our tires to make it around a banked curve at 200 miles an hour. We just need to be able to drive to work. So I'm going to give you some cut points for Kramer's V, Kendall's Tau B, Pearson's R, and Pearson's R is the tool that's normally referred to as the correlation coefficient, even though there are a variety of correlation tools. These all, I would argue, could use this basic set of cut points. I have a variety of statistics books on my bookshelf. I can pull a bunch of them down, and they disagree with this, and they disagree with each other on where they draw these lines. So these are just rough guidelines. Don't plant your flag on this hill. Don't get into an argument and say, no, I know this is these aren't magic numbers that everything is aligned with this. These are rough guidelines. So in these tools that we will see exemplified in a variety of the videos to come, you're going to see that around 0 means there's simply no relationship. One variable is not related. The patterns in one, they do not help us to understand the patterns in the other. There's no predictive ability, no association, no correlation. As you move higher, if you have a 0.1, then we're going to say you start having a very weak relationship. Now, be careful here, because you're going to be like, oh, I want strong. I want to find the real strong effects, the strong causes. Well, that's fine. But in truth, not many strong causes are out there. Think about all the factors that affect how well students do in an elementary school. There are a lot of factors. Their own innate ability, the opportunity at home to have books and computers and resources, if their parents use a higher level vocabulary, which helps prepare them to do better in school, if they have a better teacher, if they have a worse teacher, if they're in a crowded school, if they're in a school that has more resources. The list is really long. So to think that somehow you're going to find one predictor variable and say, oh, that's the one that explains everything, you're not, usually, with most of reality. So you end up saying, what we want to do is we want to look for even weak effects, right? Weak effects still can matter. So saying that once the value is over 0.1, it's very weak, and then once it's over 0.2, it's a weak effect, 0.3 is moderate and 0.5 is strong, anywhere in that range is worth consideration. It's worth thinking about it. Very weak doesn't impress us as much as weak, doesn't impress us as much as moderate, and so forth. But still, we want to be realistic about how much an independent variable can matter in a real-world situation. So we'll come back to this later. None of this will necessarily make sense as you glance at it now, but this is laying the groundwork for all the bivariate tools we're going to work with down the road, or at least most of them. Now, the other kind of effect size measures don't provide us with this 0 to 1 that is basically given on rules of thumb. The other kind gives us a series of proportions. So the other kind of strength measure we're going to see specifically tells us the proportion of variation explained. So for example, there's a tool called the coefficient of determination, which is Pearson's R squared, the multiple correlation coefficient, which is a capital R squared, eta squared. These are just names. They don't mean anything to you at this point, but we'll look at all these down the road. They also range from 0 to 1, but we don't have rough guidelines for them. We don't have rules of thumb for these tools. They have to be interpreted more in the context of what's being measured and what the question is. These tools tell us the proportion of variation in the dependent variable that is predicted by values on the independent variable. So you know that we have a bunch of people and we're trying to predict something about their happiness. And we have a series of survey questions that we believe measures how happy they are. But people vary in how happy they are, from not at all happy to ecstatically happy and everywhere in between. And so we look at this group of people and there's a lot of variation amongst them in terms of happiness. Now, can we find an independent variable that can explain mathematically, can predict mathematically, is related to that variation? Normally what we find in the mathematics behind the scene here is that independent variables can explain nothing and you're going to get a value of 0, or they could explain a great deal and you're going to get a value higher, all the way up hypothetically to 1. Although if you ever see a relationship of 1 with any effect size measure, something is really wrong. No independent variable explains 100% of the variation in a dependent variable. No single variable can do that in regular life. So when you look at this, you might see one of these tools in a later example. Perhaps we'll have an eta squared value of 0.03. That would mean that 3% of the variation in whatever the dependent variable is, 3% of that variation can be explained with this independent variable. But if we had another independent variable and we had this outrageously high 0.9 eta squared, then that would mean 90% of the variation was explained. Like I said, you're not going to see anything that high. There's only one circumstance where we can do something like that, and it's a predictive slope. But if we look at this, then we rarely will see these kinds of numbers. But these we don't say 0.1, 0.2, 0.3, 0.5. These we end up saying, with these tools, we end up saying, so what is the proportion of variation explained? Keep that in mind. You'll see examples of it when we look at things like regression, when we look at things like an F-test, those kinds of tools, ANOVA, analysis of variance, the F-test. We're going to basically be looking at the proportion of variation explained by looking at an eta squared or a capital R squared or some tool like that. And finally, we have the idea of significance. So significance is reported as a p-value. There'll just be a p, and normally in statistical output, it'll just be a p equals something, or it'll just have a reporting of the probability that's a number. Now, probability can only range from 0 to 1, and this is, I'm going to perhaps trouble some professional statisticians again by something I say here. People put too much emphasis on statistical significance. Statistical significance does one thing. It's a very important thing. It's a very valuable thing. But it only is one narrow thing. And people get confused, particularly those who are just doing basic applied work and don't realize what this tool does. They overemphasize it and believe too much out of it. But I have statistics books on my shelf that are meant for undergraduate classes and such that honestly, 80% of the book is all about statistical significance. Even though you can't answer any real questions with just statistical significance. Nonetheless, this is something that a lot of people focus on. Not as much in the last 10 or 15 years. So maybe we're not having this problem the way we were earlier 20 years ago. But it's still something to be cautious about. So this probability number is just telling us the probability that we could get the real world data we have, because you're running analysis on real data. Somebody answered some questions. We measured something that compares the different stores to each other, something that compares different states or counties to each other. Whatever our cases are, whatever our data are, we have real world data, and we see patterns in that data. All right. So this probability number says, look at the patterns in that data. And we've built a way mathematically to say, with the patterns that we have, are they far enough away from what the null predicts? Remember, the null predicts no relationship. So if you're saying men and women and their view of some particular new policy, and some percentage of men are for the new policy and some percentage of women are for the new policy, the null says it's going to be the same. They're not going to be related. Men will have the same percentage for the policy as women. It doesn't matter if that's men have 90% and women have 90%, or if men have 50% and women have 50%, or if men have 5% and women have 5%. It just means the independent categories don't in any way predict anything about the pattern in the dependent variable. That's what the null says in a bivariate relationship. Now, we can look at our data and say, what would the null say should be true in this data? And then we can look at the real world data and see how far away it is from what the null says should be true. And the p-value that is reported in statistical work is the probability that we could get this real world data even if the null hypothesis that there's no relationship is actually true. There are lots of ways this could happen, but the most common way we talk about is if you have a bad sample. Let's say that you sample 100 customers and you have 10,000 customers who come through in a month, and you sample 100 customers and you find out their view of some new product. Well, what if you have 100 customers that aren't representative? They really don't, as a group, look like that 10,000 person group. Then you might find something there and say, oh, look, we see something going on. This variable is related to that variable. But in the real population of 10,000 cases, maybe the null is true. All that's happening behind the scenes with statistical significance is a mathematical procedure to say, can we reject the idea that the null is true? That's all that's happening here. So by custom, in the social sciences, we reject the null hypothesis. We say the results are statistically significant. Those are synonymous. They mean exactly the same thing. If the p-value is less than 0.05, which means there would be less than 5 in 100 chance, or less than 5% chance, that the null could be true. So statistical significance tells us nothing about what is empirically true out there in the world. It's a hypothetical exercise that says, what we found, is it different enough from what the null predicts that we can reject the null? Or is it not very far from what the null predicts, and so we can't reject the null? So are we going to say the null is false, it's unlikely, or are we going to say that we can't reject the null? We're too close to it. That's what statistical significance does. Now, that may sound really esoteric, in a way it is, but all it really means is you look at the shape in a bivariate relationship and you say, here is the pattern of relationship between these two variables. Then you look at the strength and you say, how powerful is that pattern? So men and women had different views. Did men and women, that's the pattern. Did men and women have huge differences in views or small differences in views? That's the strength. And whatever we found, is it far enough away from this hypothetical alternate claim that there is no relationship? Is it far enough away from no relationship that we can reject the idea that no relationship might still be true? That's all statistical significance does. When you answer practical questions, you need to look at the shape. You need to figure out who's more for or against, men or women. Who's more satisfied, women or men? You need to figure out how big a difference it is. You need to find out if different advertising techniques make a difference for who buys. You need to find out if a different program helps people to find jobs better than some other program. Then you need the shape and you need the strength. And then you check and you say, if it's statistically significant, we have the added benefit of being able to say that we can reject the idea that maybe, because of measurement error, sampling error, something else, maybe the null is really true out there and we've just mismeasured or in some way missampled. So in hypothesis testing, which is a common approach to statistics and not the framework I'm giving you, statistical significance is at the heart of everything. At the heart of every analysis, you start by stating the research hypothesis and stating the null hypothesis and stating what your significance level would be, 0.05 or 0.01 or whatever it might be. And you work to answer that. I have statistics books that we're going to have the next video be about cross-tabulations. I have statistics books that barely look at cross-tabulations except to look at how you would do statistical significance for them. That's no use to a person who's trying to answer a real-world question. So I don't want to demean the importance or belittle statistical significance, but I want to put it in its place. And so I'm not going to focus on it anywhere near as much as a lot of other statisticians would, because they're trying to accomplish something other than what I'm trying to accomplish. Okay, so when you have two variable results or you have multivariate results, you're going to have to look for shape, strength, and significance. And in the videos that are coming, the next one will be on cross-tabulations. In the cross-tabulation video, for example, I need to show you how do you find the shape in a cross-tabulation. But I'm going to assume you know what I just said about compare and contrast and about direction of effect. And I'm going to say, how do you determine the strength of the effect or the size of the effect? The size of the pattern. And then for that, I'm going to assume that you now have some idea of what I mean by strength, that we sometimes use rules of thumb and that sometimes we use proportionate explanation of variation of the dependent variable. All of this will become more clear, because if this is the first time you've ever heard any of this, most of this is sounding very obscure. If all of this is obscure, it will become more clear when you see examples of it with different tools. And then I'm going to have to talk about where you see significance and what you do with it in cross-tabulations. I will do that for cross-tabulations. I will do that for a couple of kinds of comparison of means tests, and I will do it in a video that talks about correlation as a mechanism for bivariate relationship analysis. And in all of those, we'll need to look at shape and strength and significance. And this video is just meant to provide the groundwork for the conceptual and practical tools that we need to use to accomplish those things in those real applications.